Hey, juniors, it's happening. We're going to talk today about climate change, and I kind of like this image because it's pretty apt when it comes to this topic. This is a quasi-political statement. I to some extent, I'm not going to go into detail about it, but just to say that there are a lot of people, and it's a psychology thing mostly, who just don't want to deal with this. And so the best way we've been dealing with it over the last little while is to put our heads in the sand. Um, Essentially that's what denialism becomes. And the reality is that this is not a controversial issue among scientists and among most countries in the world. And so what you hear in the US is a very different story than what you hear other places, especially places where they're experiencing very, very heavily the effects of this. A good friend of mine, a good example of this is in Kenya, where I work with a school for Maasai girls. A good friend of mine, Jacob Mayani, who's Maasai from that area, will tell you all about how the seasonal shifts have changed from what the Maasai would experience normally as two rainy seasons, two dry seasons. Because they're on the equator, they don't have winter. But significant changes have occurred. They aren't nearly as predictable as they used to be, and they can be long or short, and they never know which. And typically, they were very predictable. And so these kinds of things, are the reality. I can tell you, we have much less snow in winter than we used to. I mean, I can document that. We can go back and look at climate data and look at that. And I've done that in the past, um, and that would be a fun thing to look at. Maybe we will. But those are examples. Here we're a bit more insulated because we are wealthy and we have a temperate environment that fluctuates anyway. But if you're living in more marginal areas, the Arctic, the equator, deserts, things like that, then you experience this much more significantly than the rest of us do. Or if you're on islands that don't have a lot of elevation, and places like that are already planning on leaving within the next century and having to migrate their entire populations to other countries. And so these aren't insignificant issues. And so the UN, of course, has been spearheading a lot of this, and we are a part of that. A couple of years ago, they came out with their um, with an addendum to their latest IPCC report that looked at specifically at the effects of 1.5 degrees above pre-industrial levels of 1.5 degrees Celsius, which is 2.7 degrees Fahrenheit. On average, of course, that doesn't seem like much, but it's a lot. And if you read that report, it's pretty. Some would say it's dramatic, right? And well, if you think about it, and we're at now 415 parts per million CO2 in the atmosphere, and the last time we were there, um, Williamsburg was underwater. So these are things that we should be thinking about. So let's explore this a little bit. Um, we know the globe is warming. We know that natural variability does not account for that warming. We know that human activity accounts for the warming and is changing the planet, and that includes these various greenhouse gases. At different points of the year, school year, I've mentioned this. You guys are all aware of this. The warming has consequences. The warming can accentuate, and this should actually be amplifying feedbacks and balancing feedbacks. So this is a little bit of older terminology, but there are some feedbacks that amplify the warming and make what we've already done actually a whole lot more intense. The melting of ice, for instance, leads to a darker ocean and less white colored snow, which would normally reflect more energy back out into space, and then of course it accentuates the warming. So we have to reach for sustainability. If we look at global temperature anomalies between 1880 to 217, we compare them against the decade of 1950 to 1960. We can see from 1880, the temperatures are much cooler back in those days. As you can see, it's going to become much more yellow and orange over time here as the time progresses. And watch what happens though as we get much closer to our own time. Okay, all right, we're going to cross over the comparison decade here. Now watch what happens. So we're in the 1970s, and then we're in the 1980s, and whoa, suddenly it's a lot more yellow. And now we're into the 1990s, and now we're into the 2000s, and it's going to stop here at 2015, I think, or actually 2017. And you can see how much warmer the Arctic is than it was. This is reality. This is measured temperature from satellites. Of course, this is also confirmed with data that's on the ground. This is using NASA's GISS temp instrument. So if we look at some of these pieces of data, these are directly from NASA. We look at the temperature anomaly, and we can see that as of a couple of years ago, we were already at 1 degree above pre-industrial levels, which corresponds to, at that time, about 408 part per million CO2. There is a lag, I should point out, between the temperature and the CO2. We know this quite well. You can see that both are rising upward. CO2 is pretty consistently rising upward, and it's at 415 as of yesterday when I checked it. But the temperature tends to lag behind, so it hasn't caught up. The temperature here might be somewhere, reflecting CO2 somewhere back here. So we have a lot of warming that's already baked in that we haven't experienced yet. This is the temperature anomaly as of January 2017. That here, what you're looking at are average temperatures for the year, and you can see they're going up over time, especially the last decade or so. And of course, you're going to have some ups and downs. But this has continued to go on up. 2020 has been warmer than any of these other years, and so forth. And then, of course, this is actually looking at sea ice, and you can see what's been happening to sea ice in the Arctic, been going down over time. And Antarctic mass. So this was Arctic sea ice. This is Antarctic sea ice. So you can see the ice is melting about the same rate, or in a similar fashion, an inverse negative slope compared to the positive growth of temperature and CO2 and so forth. This is the Greenland ice mass. You can see that there's a seasonal variability, right? It increases in the winters and so forth, but overall it's going down, right? And then we look at sea level change, and sea level change is going up along with the temperature and so forth. And this is in millimeters, but this is over 200 millimeters in sea level rise since 1880. 200 millimeters is a fairly decent amount of sea level rise for a short period of time. All right, and then 20 millimeters is 2 centimeters, so you're looking at quite a bit of sea level rise. Not quite half a meter, but you're getting there. And then of course the sea height variation is another way of measuring this as well. That's going up. We look at the same time at a couple of things. The ocean pH is going down. That's a result of acidification, more CO2 in the ocean. The partial pressure of CO2 is going up at the same time in the oceans, and CO2 in the atmosphere is also rising at the same time. And you can see these lines, the slopes of these lines are fairly right on the same each other. So you have a 1.9 slope over here and a 1.811 slope. And so, the slopes are the same. The increases are the same. And so, we know that CO2 is absorbed first in the oceans before it's absorbed in the atmosphere. And so ocean acidification is the sort of evil twin of global warming. And we've looked at this a little bit with corals. Corals are bleaching, things of that nature. The corals are going to have a hard time adapting to this. So the question is, what's really warming the world, right? And so this is the observed ocean and land ocean temperature here. If we move on here, we can look at where things, if it were just being driven by orbital changes, Milankovitch cycles. We mentioned these briefly in class: eccentricity, obliquity, precession, that drove the glacial periods over the last few 100,000 years, or actually 2.5 million years. This is where you'd expect those to be. And there's fluctuations in there, but they would not have been going over, your CO2 for the last 2.5 million years hasn't gone over 280 parts per million. And so you're not going to have a lot of fluctuation in climate. It'd be about right along the average. But what we see observed over here is a lot different, right? Let's look at solar variation. Solar variation has stayed pretty consistent as well. It tracks the warming roughly until about here, and then the warming really takes off. So it's not the sun, it's volcanoes. Volcanoes tend to have a cooling effect. Volcanic activity has been really better measured over here than it was back here, but again, staying very close to what average volcanic activity would be, and your temperature values are still going up. How about all three of these things combined? If we take those signatures and bring them all together into a signal, a single signal, you still see temperatures going far and away above that. How about land use change? Land use is actually should be driving things to go in a different direction. This is really getting at deforestation, essentially. So humans have cut, plowed, paved more than half the Earth's surface. Dark forests yielded light patches that reflects more sunlight and have a slight cooling effect. Now, in this case, of course, that's not happening. We're still warming. How about ozone pollution? Again, still warming, no effect. Aerosols tend to cool the atmosphere. Well, they're of course they have a slightly different trend here. So they are not offsetting the warming clearly. But if we look at greenhouse gases, this is a combination of CO2 and so forth. We see that it pretty much perfectly matches the temperature curve that we're looking at. And again, if we compare and contrast the natural and human things here, here we're looking at all the factors together versus the observed temperature, and it's pretty much all the human factors, that is, and that's what we're looking at here. So, and of course, I've mentioned the isotopic signatures of the CO2, methane, and all of that, pointing to human as well. The bottom line is humans are causing this, and where we are right now is a direct relationship is directly related to our activity on a large scale. This little video here, and I'm going to provide this slideshow so you can go and check out the video, but this gets into the question of denial. And this denial thing is a big deal. It's definitely worth checking out the video for this, but I'm not going to play it here because it's 6 minutes long. So we're gonna move on here. But the consequences of doing something versus not doing something. I've given you the basic background without going into the physics of global warming and so forth, because while we could do that, certainly it comes down to the ability of greenhouse gases to, as the sunlight comes in as shortwave radiation, it reflects back from the Earth's surface as long-wave radiation, which then interacts with the CO2 and methane particles that makes them vibrate and causes them to retain the energy. And that's why it sticks around. The IPCC came out with a report on what it would be like to have 1.5 degrees of increase. The IPCC is the Intergovernmental Panel on Climate Change. It's still around, been around since the 90s. It meets annually, and reports are created every few years. They're called the Conference of Parties reports, or the COP reports. And so every year there's a COP a COP this, COP that. It's sequentially another one every year, and we're a part of that. At least we have been. The Paris Climate Accord, which has been in the news a lot recently because we've just rejoined it, was put together and commissioned by COP21, the Conference of Parties meeting, the 21st Conference of Parties meeting. It outlines the predicted impacts of 1.5 degree centigrade increase versus a 2 degree centigrade increase, which doesn't seem like much, but it's quite significant. We have achieved one, and actually, we may have actually achieved 1.5 already over pre-industrial levels. We just haven't experienced all the effects of it yet, because they're coming. And we're not talking about long-term models. We're talking about the next few decade models. So those are really, really accurate. So it outlines measures that we can use to combat climate change and prevent a 2 degree centigrade world. And this is where we are essentially. These are cumulative CO2 emissions. So this is where things were observed in the early 2000s. This is what you expect to have in terms of temperature change at a CO2 concentration of between 430 and 480. You're looking at a value of a little over 1.5 degrees. We're at 415 right now. 280 is pre-industrial. So you can see we've come a long way. They're predicting by the 2090s for us to be closer to the 480 to 530. This is business as usual if we don't do anything. What does that mean to do something? We need to stop emitting carbon, number one. But we can't stop there. If you go into this document further, which we're not going to do at the moment, you would not only need to do that, you would need to actually be pulling carbon out of the atmosphere. Interestingly, there's a lot of entrepreneurs out there looking for ways to pull carbon out and turn carbon into other fuels. The problem with that, of course, is you're not really pulling it out permanently. You're turning it into other fuels and burning it and putting it back in the atmosphere. What you need to do is pull it out and pull it out permanently. But it's difficult because it's not only expensive. We had some students here figure out a method, and they went to the International Science Fair with it. And I don't know where it is right now, but they scrubbed CO2 successfully from the air here. But what do you do with it once you pull it out, right? You got to have an economic use for it. Otherwise, all you're doing is using tax money to pull it to pay for pulling it out. And you could do this with a carbon tax, of course. You could carbon tax people extra tax at the gas pump and places like that, where you could actually bring in enough revenue to cover these technologies. Ideally, you would come up with a use for all that carbon dioxide. Not everybody's going to go out and just play paintball, right? But even when you do that, with the CO2 cartridges, you're still putting that CO2 back in the atmosphere, so it's not doing you any good. You got to store it away. That's how the carbon cycle works. Where we've got the short-term carbon cycle, that's normal stuff, right? And then we take the fossil fuels out of the ground, which have been stored there for hundreds of millions of years in some cases. And now we're pulling that carbon, putting it back into the short-term carbon cycle. And suddenly there's a lot more carbon in the system than there used to be. And that's the problem. We got to put it back into the ground or store it some other way so that it doesn't come back, so that it's out of the system. There's various emission pathways. These scenarios are looking at, what do we do if we actually do what we need to be able to do to pull stuff out, stop burning? There is a possibility of being able to go back and decrease the global temperature and get back to pre-industrial levels. And, for the ecosystem we currently have, that's what our ecosystems are adapted to or evolved to live in, right? If we go this opposite route, which is business as usual, where we allow every country to use fossil fuels to develop and everything else, we're going to end up, before we're out of fossil fuels, we're going to end up with a situation where we've increased to almost 6 degrees Celsius. The ramifications of that are significant. We would have significant flooding along coastal cities. We'd have major food issues because, yes, you can grow plants plants like a higher CO2 environment, but not necessarily the ones you want. And then, of course, if you diminish the biodiversity that exists currently by making it impossible for the current forest to really support the trophic pyramid of organisms, you decrease the ecosystem services that we need to survive. Because we're at the top of that pyramid, we need everything below us as it is. So it's a pretty complex thing. This is another video that's worth watching. It's all about the IPCC Climate Change Report. So I encourage you to check it out in the regular version of this. This is not going to be your next assignment, so we're going to go away from that. This is where I'm going to end for the moment. One of the things we're going to do this week is look at climate change throughout the Cenozoic era. We're also going to look at ice core data from the Vostok ice core. So I'm going to end this here, but check out those other assignments, and we'll work on one of those in class for the Vostok data probably. All right, take care, guys.